Okay, so we want to finish 2.2, and then we're going to start, or hopefully go through section 2.4. Okay, so we're going to look at computing. Limits that go to positive or negative infinity. Without a graph. So one way is to look for vertical asymptotes. If you have some function f of x equal to a function p of x over another function q of x, there's a vertical asymptote q of x equals 0. And also p of x not equal to 0. So I have an example. Oh, yeah, and also hello, everybody. I hope you're having a good day. Okay, first example, f of x equals 1 over x. Okay, vertical asymptote at x equals 0. Okay, so first we're going to let x approach 0 from the right. Or no, I put from the left on your number line. Okay, so we're going to have like, let's go like -1, then -1/2, closer to 0. Even closer would be like -1/10. We'll put -1 over 100. So you put -1 in this denominator and 1 over -1. Put -1/2 in the denominator, which you're going to take the reciprocal and have -2. Same with -1 over 10. We'll flip over and have -10 right here. Put in -1 over 100. Very, very small negative number. Get out positive 100. So -1 over 100. -100 is the output. Okay. So we're going -1, -2, -10. If you keep on going and put in -1 over 1000, you'll get -1000 as the output. So it's going to negative infinity. Just put 1 over x. X goes to 0 from the left side of 1 over x. is negative infinity. Let's go on the right. So put in positive 1, put in positive 1/2, positive 1 over 10, positive 1 over 100, and get closer and closer and closer to 0. Okay, so 1 over 1 is 1. 1 over 1/2 will give you 2. This output will be 10. 1 over 100, a very small positive number is a very large positive output. 1, 2, 3, 4, 5 of these, and then your output is positive 1, 2, 3, 4, 5. So we're having our inputs are positive and getting closer and closer to 0. Some very, very small number. The outputs are getting larger and larger, going to positive infinity. Okay, x is going to 0 from the right side of 1 over x. We get out positive infinity. All right. Another example. Okay, the limit as x goes to 0 of 1 over x squared. Okay, so we're just going to kind of imagine putting in some values, some very, very small negative numbers close to 0, some very, very small positive numbers. And I'm going to write small for my very small numbers. So I have very, very small positive number. Positive number squared is positive, so this is 1 over a very small positive number. And like we saw in the last example, 1 over a very small number is going to have an output that's a very big positive number. Or positive infinity. So as these numbers get smaller and smaller, as this denominator gets smaller, the output gets bigger. Put in a negative number that's very, very close to 0, very small negative number. Is 1 over a negative small number. Oh, actually, that number is going to be squared, so it's still going to be that negative is inside the parentheses, so it's always going to come out as a positive denominator. That's very, very small. 1 over small equals big. This is starting to look a bit too. It looks weird, but it should make sense. All right, so I've got that since the limit went to positive infinity on the left and positive infinity on the right, the limit as x goes to 0. 1 over x squared is positive infinity. Cool. I have another example to help with this idea. Find the limit as x goes to 2 of, let's put this in brackets, in the numerator x plus 3, denominator has x times x minus 2. So we've got a vertical asymptote for x equal to 0, or at x equals 0, and at x equals 2. And you're approaching 2, so you're probably going to, well, we're going to work this out with our ideas that we've got. So we're getting really close to 2. Let's start with going on the left side. Some number like 1.9. Okay, so what we're going to do is the limit. X is going to 2 from the left. On the left side, I'm just going to put f of x. Equals, so it's close to 2, so about 5 right here. This is almost 2. But this is not exactly 2, it's almost 2, and it's less than 2, so the difference between some number like this and 2 is a negative number. So this is some negative small number. We have a constant over this negative small number that's changing. It's going to be a negative big number, negative infinity. Okay, we're going to take the limit as x goes to 2 from the right. Okay, so like 2.0001. So it's almost 2. Let's say that you're putting in 2 and this is almost 5. Close to 2. Now you've got a number that's greater than 2, minus 2. So this difference is positive. Positive small number right here. So it's a positive 1 over small, which is big, positive infinity. And then someone already gave the answer that since this limit is going to positive infinity and that limit is going to negative infinity, the limit as x approaches 2 does not exist. So when there's no sign, it's going from the left side and the right side for your function. I think that's good for this section. I have a side note about a special function. So after taking kind of this topic in, grad school and then in my master's program, I've seen this function a couple of times. It's the sine of pi over x, and we're going to take the limit as x goes to 0 of the sine of pi over x. And I'll just let you know right now that it's this limit does not exist. And we'll describe what's going on. We'll just draw a graph. Okay. I'm going to just consider the right side. It's kind of the same on the left side, but for the right side, for x greater than 0. Sine oscillates between -1 and 1. So this function comes over along this asymptote and then down and then oscillates, and it gets closer and it bounces and never reaches this vertical asymptote at x equals 0. So you come down, over, and closer, even closer. Every time you're getting like just a little bit closer than the last one. So it's just kind of like keeps bouncing. Actually, sorry, you never pass that part. You keep bouncing on this side, up and down and up and down and up and down, and the limit never stops. It just continues to change that number. There is no number. I don't like that. Anyway, that's just a popular function. Let's start 2.4. Okay, the precise definition of a limit. All right, so just to get started, we'll draw a picture of like some general function. We're gonna put a hole right there though. Function f. We'll call this a. And over here will be L. And we've been talking about the limit as your x values go to a of your function f of x being equal to L. So as you approach a, outputs approach L, you don't need to have f of a actually equal to L. It could happen, but you don't have to have that. So the definition. Let f be a function defined on an open interval. Okay, an open interval around x equals a. But as I mentioned, it's okay if you're not defined right at a, so except possibly at x equal to a. All right. Then the limit as x goes to a of f of x equal to L means so if you're going to be a math major, you're going to do this a lot. I probably won't test you on this. I just want to introduce it just in case you go on and take more math classes later. So you have epsilon greater than 0 given epsilon greater than 0. There exists a delta greater than 0. Such that it's an if-then statement. So first, if the distance between x and a is less than delta, and it's written mathematically like absolute value x minus a less than delta. So this is the absolute value of x minus a is the distance between x and a. So when we get the distance between x and a less than delta, we will have the distance between f of x and L less than epsilon. Okay, so absolute value of f of x minus L is the distance between f of x and L. Okay, so all of what we just said means the limit as x goes to a of f of x equals L. We're going to draw a picture, and then we're going to do some proofs. I think this is really exciting, but again, I probably won't put this on your exam. Okay, we need a picture. Actually, I put a note, so a little side note that this part the the distance between x and a is less than delta, which means that x minus a is between negative delta and positive delta. We're going to add a to both sides, so that a minus delta is less than x is less than a plus delta. So we want this, and we also want that. We want negative epsilon less than f of x minus L less than epsilon. And add L to both sides. So we'll also have this going on. When x is between a minus delta and a plus delta, f of x will be between L minus epsilon and L plus epsilon. A picture will help. We're going to draw a picture. So you have your inputs, x, outputs are f of x, input y. I'm going to have some function, let's go like, sure, f. Let's mark this right here as a. Okay, so we're going to have x approach a and think that that limit will give us this value of L. Okay, to prove it, we'll start with the positive epsilon and go L plus epsilon and L minus epsilon. So we'll start with some epsilon greater than 0. And L plus epsilon and L minus epsilon. Okay, so add some little positive number, epsilon, and then subtract epsilon. And we're going to draw also, just again, we want this limit as x goes to a equal to L, so these are going to kind of correspond to. All right, so we have what is called an epsilon neighborhood around L. Okay, so then take this, we're going to work backwards to figure out what delta, so we'll go here, down, and then go here, down. So we'll have distance from A as this delta or that delta. We'll choose the smaller delta. So I wish my picture matched a little better, but let's just say we picked a delta and then we create a delta neighborhood around A. It's like A plus delta, A minus delta. Anyway, we'll choose the smaller one, the smaller delta value, so that when x values are in this neighborhood, f of x values will be in that neighborhood. I have steps to how to get through these proofs too. Okay, we've done a picture, we've done the definition, and the steps. Okay, you state the definition, or write the statement of the precise definition. So it always starts with given epsilon greater than 0. There exists a delta. Greater than 0. Such that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. Okay, the second step is to determine the appropriate delta. If you have different choices, pick the smallest one. So pick the minimum value. Okay, third step. Oh, also I put a note, work backwards. Let's see. From work backwards from the part where you have f of x minus L less than epsilon, and you'll get, let me see, work backwards from there, you'll get some kind of delta, the smallest value for delta, and then write your proof. Okay. These proofs always start like, given epsilon greater than 0. There exists a delta greater than 0. Actually, we're going to put, we found delta. So given epsilon greater than 0, let delta equal some value. Okay, whatever number you found in step 2. And then if the difference between x and a is less than this delta, we have the difference between f of x minus L, and then you show the scratch work you did earlier, a little bit of your scratch work. And it should always end with less than epsilon. So equals work less than epsilon. Work for scratch work, or just put like dot, dot, dot. And then it should end with less than epsilon. All right, first example. We're going to prove that the limit as x approaches 5 of x squared is, what do you think it is? Guess.
25.
Yes. Cool. So we're sketching the graph. Okay, so we're approaching 5, and we've got a limit of 25. You know what? I'm going to put a little extra to this problem. Prove this limit is equal to this for epsilon equal to 1. So we'll create an epsilon neighborhood, go to 26 and 24. Actually, I'm kind of missing the first part. Okay, I've got epsilon equal to 1. There exists a delta greater than 0. Such that when the difference between x and 5 is less than delta, the distance between x squared and 25 will be less than epsilon. Okay, next we get delta. All right, so we're gonna go and get the input that gave us an output for 24, so the root of 24. And this x value was the root of 26. Ooh. Okay, we're looking for some delta. So we want delta to be the smaller distance between 5 and root 26 or 5 and root 24. The root of 24 is 0.101. Root 26 is 5.099. So from here to here, the distance from root 24 to 5 is, I've got 0. Oh, I'm sorry, that's the differences. Okay, sorry, that was the distance. Root 24 is the number 4.899. Root 26 was 5.099. And then the distance from that number to 5 is 0.101. Here. And then the distance from 5 to root 26 is 0.099. Okay, so delta is the min between 0.101 and 0.099. Smaller of those numbers is 0.099. And then we write the proof. All right, hopefully you've got this sketch down, but I need space to draw everything. So 1 equal to 1. There exists, or we're going to let, I keep saying that, let delta be 0.099. Then the distance between x and 5 is less than delta. It's between x squared and 25 less than. That's the end of the proof. Some people put QED for the end of a proof. Some people draw a little filled in square on the side. I think we'll try that. There's 5 minutes left. Okay, I'm going to introduce the next problem we're going to prove, and then we'll probably come back next time to finish it. So. I prove that the limit as x approaches 2 of 3x minus 1 equals 5. So let's at least start this problem. First part, given epsilon greater than 0, there exists a delta greater than 0 such that okay, the linear f of x, 3x minus 1. And put in L, the limit is 5. Keep working, so 3x minus 6 inside absolute value bars. I'm going to factor out 3. It's positive 3. Absolute value of 3 is 3, so you could bring out 3. Absolute value of x minus 2. Actually, this whole time, let's see. Okay, so the and want. We wanted this to be less than epsilon. Okay, we're going to get this absolute value of x minus 2 less than epsilon over 3 by dividing both sides by 3. is difficult to write, but it's epsilon over 3. And this is what we kind of, have. The distance between x and 2 less than this value will be delta. So let's choose delta equal to epsilon over 3. Oh, I think I jumped around and I put the first step and the second step together a little bit. Well, let's end there. As a good scratch work, we'll come back and we'll write up this proof. Maybe we'll just walk through it one more time. And that's it for 2.4. So I'm going to post your 2.2 homework tonight. I will make a 2.4 homework soon.